Okay, today I'll be discussing of two experiments, right? Two experiments. Both experiments are based on sonometer. So this is a very frequently asked question. The questions based on sonometer. So you must have a good understanding of the sonometer, right? Okay, so write down 12, 13 sonometer. So sonometer, it has a hollow wooden box. It's like this. You can draw this with me. You can draw this with me, right? So this is a 3D sketch. So inside this box is hollow and it is wooden. There are two holes, two or three holes. So the sound can come out of these holes outside, right? So this is like a similar to a guitar box, right? So on this sonometer, sonometer box, we call this a bridge or peg. Then there are two nails. So this bridge is, we cannot move this bridge, or we call this peg. So it is a immovable bridge, or we call that peg, right? Then there are two movable pegs like this. Then there's a pulley here, and a string goes over these two bridges and over this pulley, right? On these pans, you can put weights or loads. So you can change the tension of this string by putting loads onto this pan. Then there's another string like this. And it is connected to a screw here. So you can rotate this screw and increase the tension of this, increase or decrease the tension of this string. So those strings are A string, let's say B string, right? A and B strings. Let's say weight is mg, then the tension capital T. So these are immovable pegs. These are movable, right? Movable bridge. Both are movable, right? So by changing the distance between immovable and movable bridges, you can change the length of this vibration. So the vibration happens within these pegs, okay? So by changing that, you can change the length. Length means vibrational length, okay? Right. So this is a screw. So when it comes to these experiments, another important thing is tuning fork, right? Tuning fork. So for these practicals, we need a tuning fork or set of tuning forks. So if you think about a tuning fork, you should be able to name these parts. So these two parts are called prongs, and this is called stem, right? These are prongs, and this is called stem. So those are the main parts of the sonometer and the tuning fork, right? Okay, take it down and thumbs up once you're taking down. Here you have a pulley, it is not drawn clearly. you have a pulley here, right? This goes over a pulley, a smooth pulley. Then I'll explain about A. Below write string A, right? Write down tension can be fine adjusted. Tension can be fine adjusted using the screw. Tension can be fine adjusted using the screw. To the same line, write value of capital T, meaning tension, right? Value of capital T is not known. Value of capital T is not known. Quickly take the notes, right? Then if you think about B, in front of B, right? Tension can be changed. Tension can be changed within brackets T equals mg. So the tension of this string is always equal to mg, whatever the load you put here. Tension can be changed, T equals mg. Its value is capital Mg. Its value is capital Mg. Okay, so when we are doing experiments using this, so for these two experiments, I am going to use one of these string, right? Let's say A. So the main equation we are using, this is like F equals ma in mechanics. So for waves, we use this equation, right? V equals F lambda. So I'm applying this equation to the wire. So when you apply that, you know that this is a string. Speed of waves in a string. What is that? V is equal to tension divided by simple m. Simple m means linear density, right? So this is mass divided by length. If you want, you can take this down. Mass divided by length is simple m. Then this is tension. So velocity is, you can write this, T over m root equals simple f. That's the frequency which this wire vibrates. And for lambda, we can vibrate this at any overtone, right? But usually we use the fundamental for these experiments. Since we don't know, I'll just put KL. So this is like lambda divided by K is equal to L. So lambda becomes KL. Okay, take this down. Below this, right? Just take down notes as I'm explaining, okay? Below this, right? By changing capital M, or simple L, capital M or simple L. Simple F can be changed. Simple F can be changed. Then write simple F is the frequency that the wire likes to oscillate. Simple F is the frequency that the wire likes to oscillate. Within brackets, right, in front of that, resonance frequency. Resonance frequency. Resonance frequency, you know resonance, right? Resonance frequency. Right. So at the resonance frequency, what happens? This wire will vibrate with the highest amplitude, right? It will have the highest magnitude. That's what happens at the resonance frequency. So if you remember the experiment, if you put a paper rider on this wire, so at the resonance frequency, it would fly away. Because at that point, if this has the resonance frequency, this will have the highest amplitude, right? Highest amplitude. So the wire would, paper rider flies away, right? So you have to clearly understand this stuff, right? So this is simple if. Likes to vibrate means, let's say, if you place this tuning fork, you can hit this tuning fork on a rubber block and place this here. At the same frequency, the wire will vibrate. Let's say, for an example, if this has 100 hertz, when you place it here, the wire also will vibrate at 100 hertz. But it does not mean that wire likes to vibrate at 100 hertz, right? Let's say wire likes to vibrate at 150 hertz at this point, at this instant. It will vibrate, but it won't have the resonance because the frequencies are not matched there, right? Then by changing the length, by moving these bridges, you can change these lengths and change the frequency to 100 hertz. Then there will be the resonance. Okay, I'll explain that further. So this is all about the sonometer and the tuning fork, right? Then we have to think about how to do a tuning. You have heard tuning, right? So there are 3 ways that you can tune. What does tuning mean? Write down like a subtopic, tuning. You have heard this many times, but let's exactly understand what this means, right? So you know that when 2 things are in tune, meaning the tuning fork and the wire, if they are in tune, obviously the frequencies of them should be same, right? Let's say this is a frequency of wire, this is frequency of fork. So the frequency should be same if they are in tune. So we say this is tuned. But we cannot exactly say that, right? If the wires are tuned, obviously the frequencies are same. If 2 things are in tune, you cannot say the frequencies are different. They must have the same frequency. If wire and the fork are in tune, frequencies are the same. So this is true. But if frequencies are the same, we cannot necessarily say that 2 are tuned. So what is the another requirement? Just frequencies being same does not mean that wire is in tune. If those 2 are in tuned, wire must have its resonance, right? So when you place 100 hertz here on the wooden box, the wire also has the 100 hertz, but it doesn't mean it is tuned, because 100 hertz is not the frequency of wire that it likes to vibrate. The wire doesn't like to vibrate at 100 hertz, so it doesn't have the resonance, right? It might have 150. So if you put a 150 fork here, then they will have the resonance, right? Right. Just write this one, and below that write as points. When fork is placed on sonometer box, when fork is placed on sonometer box, comma, sonometer wire oscillates, sonometer wire oscillates at the frequency of fork, at the frequency of fork, comma, by forced oscillation, by forced oscillation, right? And now listen. So that happens when you place the fork here. It should not be in contact, right? It should only be in contact with the box. When you place it here, the wire also vibrates at the frequency of the fork, let's say 100 hertz. But we call that, what do we call that? We call that forced oscillation. Remember theory parts? So that is what we call forced oscillation, not resonance, right? So what do we have to do? We have to change the length of the wire and make the frequency of the wire to be equal to the frequency of the fork. Then they will have the resonance. Okay. Okay. Write down next point. Next point. This does not mean they are tuned. This does not mean they are tuned. Another point. In order to be tuned, wire should be vibrated. Wire should be vibrated at its desired frequency. At its desired frequency. Underline desired frequency. At its desired frequency, comma, resonance frequency. Then only resonance occurs. Then only resonance occurs having the highest amplitude. Having the highest amplitude. Right. I think now you have a exact idea of tuning, right? Tuning. Then we have to talk about ways of tuning. There are mainly three types, three ways to tune, right? To do what I just said. Write with me, three ways of tuning. Three ways of tuning. So the first one, write with me. First method is resonance, right? Second one, using beats. You know beats, using beats. Third one, by hearing, right? By listening to that. Musicians can do that, right? We cannot do that. Musicians can compare frequencies just by hearing, right? Whether they are the same or not. Right. Then I have to talk about resonance. Write the subtopic resonance. Okay. Now I'm only talking about just a one wire, right? We don't need yet this wire. I'm only talking about a one wire, right? So what do we do if you need to tune using resonance? You need the fork. Let's say fork has 100 hertz. It doesn't, right? But let's say it has 100 hertz. You have to hit the prongs of the fork, prongs, right? Not the stem, prongs of the fork On a rubber block, you are not going to hit it on like other surfaces, right? Because it would damage the fork. So you, in the lab, you have a rubber block. You can hit the fork on the rubber block and vibrate that, right? So that's the first thing. Then you have to place it here, like this, right? Then when you place it here, let's say 100 hertz, fork has 100 hertz. It has a certain frequency, right? It cannot vibrate at other frequencies. So the fork vibrates at 100 hertz. So by forced oscillation, the wire also vibrates at 100 hertz, right? But still resonance does not occur, right? Then what do? Remember, you applied this equation to the wire, right? So the let's say the desired frequency at this moment of the wire is 100 hertz, but the fork has a 100 hertz, right? This is 150. So in order to have the resonance, what should we do? We have to decrease the frequency of this wire into 100 hertz. So to decrease, what can we do? If you think about this equation, the easiest one to do is you need to decrease frequency, right? Natural frequency of the wire. So you can increase the length. You can increase that by moving this movable length to this side, right? So that is one way. That is the easiest way. Another way is if you need to decrease the frequency, you can decrease the loads. Loads here. You can remove the masses from here. Then you can decrease the frequency. So either way, you have to decrease this to 100 hertz. Now both wire likes to move at 100 hertz. So we changed its natural frequency to 100 hertz for the wire, right? Okay, now they are matched. Both have the 100 hertz and this has its desired frequency, the wire. Then what happens? Then resonance occurs. So it will have the highest amplitude, meaning if you place a paper rider, it would fly away. Right. So you wrote resonance, right? Resonance. Under that, right? Vibrate. Under resonance, right? Vibrate tuning fork. Vibrate the tuning fork by hitting it on a rubber block. On a rubber block. Within brackets, to prevent its prongs, damaging. Right. Another point. Then place the stem of fork. Place the stem on fork. Stem of fork on sonometer box. On sonometer box. Within brackets, right? This causes the wire to forced oscillate at the frequency of fork. Forced oscillate at the frequency of fork. Okay. Now listen. Now you place the fork, right? You place the fork, tuning fork. Then the another thing is, so they are asking the exam, there are many ways you can place this fork, right? This is one of the way. Let's say this is the sonometer wire. This is sonometer wire, right? You can place the fork like this, a vibrating fork. Then what happens? The prongs will vibrate, and through air, it can transfer energy to this wire. But it is very inefficient, right? Inefficient. Why is that? Because there's a third medium here. Air is not a good medium to transfer energy, right? So these will vibrate as sound waves to the wire. But it is very inefficient way of energy transfer, right? Draw this. Below that, right? Inefficient energy transfer. So this is a very inefficient energy transfer. Then another way, you can directly place the prong on the wire. Here what happens? Remember resonance, right? This wire has to vibrate at resonance. But here it is not free to move, free to have that at resonance, right? So here what happens? Wire is not free to oscillate. Wire is not free to oscillate. So both methods are wrong. Take it down, right? Both methods are wrong. Then there's the third method. Let's say you have, this is the surface of the wooden box, sonometer box, surface, right? You have to place the stem like this and the prongs like this. Then there's the wire. The wire is in front of or behind, right? Wire is behind, not contacting with this one. Then what happens? So you are placing it somewhere here on the wooden box. The energy transfers through these pegs, through the wooden box, into the pegs and into the wire. So the energy transfer happens in a solid. So it is a very efficient energy transfer. So if they ask in the exam, that is what you have to say, right? Below that you can write energy of fork transfers to the wire. Energy of fork transfers to the wire efficiently. Take down the notes as I'm explaining, right? Okay, now what has happened? The wire is forced oscillated using the fork, but still not, the resonance is not gained, right? Then another step, write down below that, right? Adjust simple L or capital M. Adjust simple L or capital M to get the required resonance. To get the required resonance, comma, so it matches with frequency of the fork. Frequency of the fork. Below that, right? Then the wire and the fork are tuned. Wire and the fork are tuned. Below that, right, another point. The paper rider would fly away. The paper rider would fly away. Okay, so that is resonance, right? So that is resonance. Then the second one, beats, right? Using beats. So let's say this is the wave pattern in the wire. Sorry, a fork, let's say fork. And the frequency is F1. Then the another one is wire, right? Frequency is, let's say, F2. It has a wave pattern like this. Wire and the fork has F1 and F2 frequencies. So here you have to oscillate both simultaneously. So as you are hitting the fork on the rubber block, you have to plug this one, right? Plug this wire, and you place it closer. You are not contacting the fork on the box, right? You are just placing it like this. You are listening to the sound of both, sound of wire and sound of fork. You are vibrating them simultaneously. So let's say frequency of this one is 100, 110. Frequency of wire is 100, 100. Not 100, 100, 105. Then what do you hear? Then you are going to hear a beat frequency. So the beat frequency is the difference, right? F1 minus F2, that is 5. You are going to hear a beat frequency of 5 Hertz. If they are close, right? So when these two superpose, just draw this as I'm drawing, right? When these two superpose, the beat frequency is like this. So one of these is called beat, one beat. You hear a higher and lower sounds, right? So this is lower sound, then higher, then again lower. So beat frequency 5 Hertz means such sounds per second you hear 5 times. So if the beat frequency is more than 10 Hertz, then you are not going to hear any beats, right? So that's what happens, right? So beat frequency called FB, F1 minus F2. Just take the magnitude of the difference. Okay, take this down. Then write to here, beat frequency should be less than 10 Hertz, right? These are theory, right? I'm just recalling you those. FB, that should be less than 10 Hertz. Put a star mark here. Put a star mark here. This is the most accurate. This is the most accurate method. This is the most accurate method for tuning. This is the most accurate method for tuning. Full stop. But this is difficult to do. But it is difficult to do. Right? But it is difficult to do, right? So when you try to do this in the lab, right, that frequency you will not hear that with the other sounds. Those beat frequencies are not, you are not going to hear that much well, right? So this method is not somewhat, it is difficult actually, right? That's why we use that paper rider method for resonance. That method is not that accurate because you don't know at which point exactly that paper rider is going to go away, right? Fly away. This method is less accurate, but it is easy, right? This method is not easy, okay? Right. So what should you do? You have to make sure that these frequencies are the same. Now you are going to hear a beats, right? Then what do you do? You have to change the frequency of the wire by changing the length or the load. Then once they matches, what happens? F1 equals F2. Then beat frequency is going to be 0. When the beat frequency is 0, then we say, these are tuned, right? So this is a very accurate method, but difficult, right? We can exactly say whether they are tuned or not here. Because, yeah. Okay, below this write, quickly write, right? Vibrate, fork and wire, vibrate, fork and wire at the same time. Vibrate, fork and wire at the same time. Another point, change the length of wire, till beats are heard. Then the third one, further change the length, till beats disappear. Or not heard, right? Till the beats are not heard, right? Okay, so let's say, so for the fork, let's say 100 hertz, right? So if the wire, this is fork, right? Let's say this is wire. Don't write this. For fork, let's say 100 hertz. And for the wire, let's say 112 hertz. For the wire, 112 hertz. Are you going to hear the beat frequency? So when you take the difference, what is that? It is like 12 hertz, right? 12 hertz of beat you cannot hear, right? Then what do? You decrease the frequency of this wire. So for that, you need to increase the length. See that? Length and frequency. To decrease the frequency, you have to increase the length. Then the frequency decreases. So once it comes to like, let's say 108, then you are going to hear 8 hertz of beats. Now the difference is 8 hertz of beats, right? Then you cannot just, now still they are not the same, right? You have to further increase the length by moving this bridge. Now this is a fine adjustment now, right? Fine. Then further, after a while, then it becomes 100 hertz. Now again, you are not going to hear beats, meaning the frequencies are the same now, right? So that is how you resonate. This is not a resonator, tuning. This is how you would tune using beats, right? This is the exact method. Okay, then write down third one, by hearing. Hearing or listening. So for hearing as well, you are not going to place the fork on the box, right? Same as beats. Again, you are listening to this one at one time separately, right? You plug the wire and listen to that carefully, the frequency of that wire. Then you plug the fork or the wire, fork, you listen to that. Then a musician, we cannot say that actually, right? A musician can say whether these two have the same frequency or not. So that is how they tune those musical instruments, right? Have you seen that? Like, so when someone trying to tune a guitar, they asked the one having the organ to play C, right? Then by listening to that, he remembers that frequency of C. He identifies that. Then by remembering that, listening to that, he fine tune his guitar into C. So the musicians can do that, right? Okay. So that's it, right? So the sonometer, we discussed about sonometer. Then we discussed about tuning of sonometer with fork, right? Then we can move on to the practicals. Write down 12. This is the 12th practical. Write down the topic. Finding unknown frequency. Finding unknown frequency of a tuning fork. Finding unknown frequency of a tuning fork. So now carefully understand what that means, right? So you are given a tuning fork, but you don't know the frequency of that, right? So when you hit that on a rubber block, it vibrates, but you don't know the frequency of that. So using the sonometer, we are going to find its frequency. So that is what we are going to do, right? Right. So you have a fork, frequency is not known. So you have a fork, frequency not known. I'll draw the simple sketch of the sonometer. This is a cross section, right? So you have these pegs. So we are going to do this experiment at the fundamental. We call this wave pattern fundamental. Then these attached to here. Another part is attached to the pulley. It goes over the pulley. And we have the weights here. Let's say mg. Then the tension is T, which becomes the tension of the wire. Right? So frequency of the fork, we are going to use find that using the sonometer, right? So for this as well, we use resonance method, okay? Right, just draw this one and thumbs up once you take it down. Right, you can take down this as I'm explaining, right? Okay. Below right, so wait. So we are going to calculate once these are resonated, we are going to calculate the frequency of this. We have methods to calculate the frequency of this, right? Using equations. We have equations. But for this, we don't have equations. For this, we have equations. So if you calculate the frequency of this wire, and if they are in tuned, we know that the frequency of fork should be that frequency. So that is what we are going to do. Okay, write down for fundamental, resonance, fundamental resonance, frequency of transverse stand-in wave, in sonometer wire between pegs means bridges, between pegs, comma, right. So what does this mean? Wire between the pegs, we are going to apply V equals F lambda. It is like applying F equals ME, right? Here, this is V equals F lambda. I'm going to apply to this wire. For the fundamental, this is the fundamental, right? We have to make sure that this is the fundamental. Okay, so let's apply that. V equals F lambda. So the V is tension divided by linear density. So tension is equal to mg, right? So instead of tension, I can put mg. Then linear density, simple m, root, equals F. What is lambda? So we are having the fundamental. Fundamental means, so this is a full wave, half of that wave, right? For the standing wave. So half of that wave is equal to length of the string. Then we can say lambda is equal to 2L. So instead of lambda, I'm putting 2L. Another equation for linear density, we have this equation. I mean, mass of string divided by length, or cross section multiplied by density of material. Just write this down and thumbs up. If you have any problem regarding these equations, let me know. Now we have this equation, right? So what do we have to do? We have to find this simple F. Simple F is the resonance frequency of the wire, right? But since it is resonated, it is also equal to the frequency of the fork. So if you found this, meaning you have found the frequency of fork. If you found the frequency of the wire, you have found the frequency of fork. Okay, simple L, you know that simple L. You can measure this length and find simple L. Linear density, you can find that using this equation. So that is mass divided by length. Or you can measure the cross section of the wire. You need a piece of wire, right? Like wire sample of this. Then you can measure the cross section and you know the density. Let's say copper or something. You know the density of copper. Then by multiplying that, you can find the linear density. Then simple M also is known. G, we know that. Capital M, we know the load applied here, right? So in the experiment, you have 500 grams of loads here. You put in those loads, right? So you can directly get the load applied. So if you know all these values, only thing you don't know is the frequency. Then you can calculate the frequency using the equation, right? So that is what we call a direct calculation. That is a direct calculation. Just using one set of things, we can calculate that. But here we are going to use a graphical method. We are going to draw a graph. So remember the last two practicals I discussed about graphical method, right? So in order to find a value, why do we use a graphical method? Even though we can calculate it using just a direct calculation. The reason is you need to minimize random errors, right? That's why you use a graphical method for this. Other one is when you need to verify something. When you need to verify an equation, then also you have to find a graphical method. But here you need to find a value using the graphical method. The purpose of that is to minimize the random errors, right? So that's all you have to say if they ask that in the exam, to minimize random errors, right? Okay, write down, below this write down, direct calculation, a direct calculation can be done, a direct calculation can be done to find simple f. Direct calculation can be done to find simple f. But a graphical method is used. A graphical method is used. Within brackets, right? To minimize random error. To minimize random errors. Okay? To minimize random errors. Right. Right. So then I am going to draw a graph, right? Graphical method. Listen carefully. So this is the equation. V equals F lambda. For lambda we got 2L, right? So when you are drawing graph, looking at the equation, you have to identify x and y, dependent and independent variables. Dependent and independent variables. So when you look at this experiment, you have to think about which one you can easily change. You only have a one fork, right? So you cannot change the frequency. In this experiment, this is not a variable. This is a constant, okay? Because you only have a one, you are going to find a one value. So f is not a variable. Simple m doesn't change, right? Simple m doesn't change. It is just the linear density. We cannot change that easily. G does not change. But we can easily put loads, apply loads onto this pan, right? Then you can change the tension easily. So that is what we do. So M, capital M, is what we call X. The thing that we can change easily, that we change, right, is what we call X. What is X? That is independent variable. So when you change X, M, this L, something has to change, right? So this L changes. This resonance length, L is what we call resonance length. Resonance length changes. So for Y, we can choose simple L. It could be 1 over L or L squared or something like that. Somehow, L is related to dependent variable. Dependent variable. You can take it out. Okay. So capital M is within a root, right? At the last experiment, for the time, oscillations of time, time period of a simple pendulum, do you remember we squared both sides, right? What's the reason? To increase the accuracy, right? There's a reason for that, right? So if they ask in the exam, this is just to increase the accuracy. That's what you have to say. F is squared for L is squared. Square the both sides. Then you have to separate capital M, that is x, right? Write other stuff here. Simple m, put simple f squared here. 4 also. This is capital M. L squared. So what do you get? L squared equals G divided by 4m f squared capital M. Now we clearly have y equals mx. So L squared is going to be y, and this is going to be gradient. I'll say m dash, right? Because this also has m. In capital M, that is simple x, dependent variable, right? Take it down and thumbs up. So this is the theory, right? This is the theory. Then we need to get, for the graphical method, we need to get a bunch of values for dependent and independent variables, right? So we need to have a table. Capital M, simple L. So you change capital M, right? Load here, you change, let's say you put 0.5 kilogram. And then you vibrate this and do the resonance. I explained that earlier, right? Do the resonance, and there's a paper rider that flies away, those stuff, right? Then you can measure the resonance length. So for 0.5, you have a resonance length, let's say 5 centimeters, right? Likewise, you just increase the load you are putting here. And let's say you need to take about 6 readings for M and L in order to draw a graph. Then using these details, what do? We go for the graph. We go for the graph. So y is L squared, x is capital M. Then you mark these coordinates, M and this is x and y, right? Let's say it is like this. You got coordinates like this. Then you draw the best fitted line. If the best fitted line goes through and it is a linear line, I mean it is just a straight line which goes through the 0, then what can we say? If it goes through the 0, this y equals mx is proved, right? Not proved, I mean it is correct. Just take this down. You go for the table, then for the graph. Right. Right. So we draw the graph, right? Let's say you got y equals mx. So when you are doing the experiments, you might not get a graph like this, right? You might get something like this. Then what do? You have to redo the experiment, right? There are some major mistake that you have done in the experiment if you get a graph like this. So you have to redo the experiment. Now being more careful, right? Till you get a graph like this. These are not as easy as we are just discussing, right? When you are doing the experiment. So that's why it is very important that you do the experiments at the school, right? If you have the chance there. Right. If not, okay. Right. So we drew the graph, right? We drew the graph. So from the graph, we are going to find the frequency. What can you extract from the graph? You can calculate the gradient, right? Gradient, which is m dash. Using the graph, you can calculate the gradient. So the gradient is equal to what? This one. G divided by 4m f squared. You know the value of gradient. You can calculate the value of gradient, right? G, you know the value. Simple m also you know the value. Only value is f squared. So using this one also you can find simple m, right? Sorry, simple f. Then we have a problem, right? So this theory is built thinking that the wire vibrated at fundamental frequency. Fundamental frequency means, so the shape of the wave pattern should be like this. But exactly we don't know that, right? You know, this has overtones. First overtone, second overtone, like that. So the wire could be vibrating at these ones as well. We don't know whether it is fundamental or not. So to make sure that this wire vibrates at the fundamental frequency, there's a method, right? Just write down this. Write down how to make sure that the wire vibrates at fundamental frequency. So this is the method, right? Within brackets, write move the pegs closer. Move the pegs closer. Full stop to the same line, right? Place vibrating fork. Place vibrating fork on sonometer box. Place vibrating fork on sonometer box until resonance occurs for the first time. Resonance occur for the first time while increasing simple L. While increasing simple L. So I'll explain this. I think I know you didn't understand that, but writing that is enough, right? Writing this will be enough. If they ask how to make sure that it vibrates at fundamental, so you have to bring the pegs closer, right? So the vibrating length is minimum. Then you place a sonometer, and there's the paper rider. While vibrating, you are placing the sonometer again and again. You keep increasing the length. At a certain point, the paper rider flies off. Then there's the resonance. So for the first, if it flies for the first time, then we can say it is the fundamental frequency. That shape, right? Not an overtone, just the fundamental frequency. You can think. So that is what you do there. But I'll explain that further, right? To have a precise understanding of this, using an example. Let's say you have the tuning fork which has 100 hertz, but you don't know, right? You don't know that. You still don't know that. Let's say it is, 1000 hertz. That's the frequency of tuning fork. So what are the variables? Capital M, right? Load you put in and the length. M and L are the variables. So we are going to change these. So let's say at first you put a 0.5 kilogram load onto the pan. Then you bring these pegs closest. Let's say F naught is the fundamental frequency of the wire. Let's say it is 2000. Then we have first overtone, that is going to be 4000. Then 3F note, that is going to be 6000, right? 3 times the fundamental. So these are the overtones, right? These are the overtones that this wire can have. You have this fork, it has 1000 hertz, but when you place it, if these are the cases for this length, for the minimum length, can there be a resonance? You cannot, right? Because this is 1000, the minimum frequency that this wire can oscillate is 2000. You cannot have a resonance. Then what do? So this is the equation, right? Then what do? You need to match the frequency of this wire with 1000 hertz. So you have to increase, right? You have to increase the length of the wire, so the frequency will decrease. Let's say you increase that. So you increase the gap, right? Gap between bridges. And let's say you get a fundamental like 1500. Then this could be 2 times. This is 2 times, so 3000, 4500, right? Still you don't have the fundamental frequency. Then what do? Then you further increase the length. Let's say now you got fundamental frequency of 1000. Then other one is 2000. Other one is 3000. Right? Now what's the case? Now you place the fork and the paper rider flies away, because there is the resonance. This 1000 and this 1000 matches up. Right? This 1000 and this 1000 matches up. So all this is done thinking that capital M is half kilogram. Right? Load applied is half kilogram. Right? Right. So now what we found? Just a one coordinate. X coordinate is M. You need to fill the table, right? For M and L. X coordinate is half kg. L coordinate is whatever the distance you measure here. Resonance length. Resonance length. So you put that here. You just got a 1. Then again what do we do? You increase the capital M, right? Let's say now you put another half kilogram. Now the mass is 1 kilogram. Mass is 1 kilogram. If you keep the same length, right? Now the length is same. Capital M, you increase the capital M. Length is same. Simple L is same. We are keeping the simple M same length. But you increase the capital M. Load apply, because now it is 1 kilogram. Now what could happen to the frequency? If you keep this same constant, you increase capital M, natural frequency increases. Now the frequency could be like, let's say, it has to increase, right? 1200. And overtones 2400, 3600. Right? Now you increase the load applied. Can there be a resonance? Can't, right? There's no 1000 hertz for the fundamental. It is 1200. Now what do you have to do? You have to increase length again to find the next coordinate. So when you increase the length, frequency decreases. This 1200 decreases to 1000. It can decrease to 1000. You have to do this till it decreases to 1000, right? Then the overtones are 2000, 3000. Now matches. Then what do? You measure this length. So this is going to be the second coordinate. Now the mass is 1 kilogram, length is, so that is the second coordinate. Likewise, you have to find 6 coordinates in order to draw the graph. Okay? Right. Write down. You again have to observe this, right? I think you might not have this is somewhat complicated. You might not have a perfect understanding. Just again think about this, right? Right. Write down this. Theory is built considering that sonometer wire vibrates at its fundamental frequency. That can be confirmed using the note below. Okay. Take down everything. You can later check this, right? Again. Once you're done, thumbs up. You need to have this in-depth understanding, right? So you can answer any question they ask, right? Regardless of how difficult the question is. You need to take these lengths same, right? That's why I have drawn these dashed lines. This length is larger. You have to show that. Okay. Jaffer did still right. Everyone right? Okay. Okay. So this is what we are doing in the experiment, right? So you need to have this in-depth understanding. You can revise this, right? Right. Another point. So for gradient, we got this, right? We got this. Take it down. M dash equal to this one. So these are usual stuff. So M dash is known, right? From the graph, always you can take a value for M dash. Below right, this experiment can be used to find simple g. If frequency of tuning fork frequency of tuning fork is known. Frequency of tuning fork is known. So if you know this one, you can calculate G, right? If you know this earlier, I mean, if you have a known tuning fork, you can find the G, right? So they might ask, using the sonometer, calculate simple G. So that is a creative question, right? So you have to remember that. Not remember, I mean, if you understand that, so there's a way to do that. But the purpose of this experiment is not to find G. Purpose is to find simple F, right? But if they ask, so there's a way, right? So they are not going to ask the same question, right? They will be creative when they're asking questions, right? Then another point, this is a normal point, right? Another point, when tension of wire is considered, mass of pan means on the balance, and hook, mass of pan and hook should be added. Got it? So there's a hook, right? And there's a pan. Without applying any loads, there's a hook and a pan. This is where you put loads. So the tension is actually is not just the load, right? 0.5 kilogram. You have to add 0.5 plus the hook and the pan, right? That's a simple fact. So that is the 12th practical, right? That is the 12th practical.